And then the consequence of having these three quantum numbers, when you solve that differential equation, remember we talked last time where those quantum numbers come from. When you solve a differential equation, as you will when you do 1803, right? Those quantum numbers come from imposing these boundary conditions on your differential equation. Those boundary conditions make a generic or general differential equation specific to the problem you're working on. And when you do that, those quantum numbers fall right out. All right? And again, we believe them to be true because they agree with our observations of nature. All right? Okay. So now we got to deal with three quantum numbers that are going to have to then describe these states that we talked about last time. So, for example, we talked about the ground state. N is equal to 1 here. But what I'm saying to you now is that there are a few more quantum numbers that we have to add to label that ground state correctly, or to label it completely. And I just said if n is equal to 1, well, then we learned about L here. L, the largest value it can have, is n minus 1. So we have a quantum number L that's tied here, and that quantum number is 0. L is equal to 0. And we just learned that we have a third quantum number M, and the greatest value that M can have is plus L. So if L is 0, then M is 0. Oh, can you see that? Yeah? Okay. And so therefore, our ground state, the label that we got to put to our ground state is the 1, 0, 0 state. All right, so we're expanding our definition of the label of that state. Yes, the last time it was n equal 1. Now it's 1, 0, 0. And then if we have an electron in that 1, 0, 0 state, then we're going to have a wave function that describes that electron. That electron is going to be represented by a wave function. That wave function is psi 1, 0, 0. All right? The energy of that 1, 0, 0 state is minus the Rydberg constant over 1 squared, just like we had last time. All right, now, suppose we have the first excited state, which was n equal 2, as we looked at last time. If n is equal to 2, what is the smallest value that L can have? Smallest value that L can have? 0. And if L is equal to 0, what's the only value M can have? 0. So we have now a state that is the 2, 0, 0 state. And if you have an electron in the 2, 0, 0 state, well, we're going to describe that electron by a wave function that we're going to label psi 2, 0, 0. And the energy of that state we saw last time, minus the Rydberg constant over 4. All right, but if n is equal to 2, we also just saw that the quantum number L can have another value, and that is 1. And if L is equal to 1, what is the largest value that M can have? 1. And so we've got another state here. It's the 2, 1, 0, 2, 1, 1 state. And if you got an electron in the 2, 1, 1 state, hey, that electron is going to be described by a wave function that we're going to call the psi 2, 1, 1 state. The psi 2, 1, 1 wave function. Notice that the energy of this state is still minus the Rydberg constant over 4. It is the same as the 2, 0, 0 state. These two states are said to be degenerate. Degenerate means have the same energy. All right, so if n is equal to 2, and then L, of course, can be equal to 1, what's the next smaller value that M can have? 0. So we have a 2, 1, 0 state. If an electron is in that state, the wave function describing that electron is 2, 1, 0. Again, the energy here is minus the Rydberg constant over 4. Same energy, because the energy is only dictated by the n quantum number. And then finally, what's the smallest value m can be if you have n equal 2, L equal 1? Negative 1. So we have a 2, 1, negative 1 state. The wave function describing that electron in that state is the psi 2, 1, minus 1's wave function.